final topic in this chapter is transformers. In the beginning of the chapter, I have told you about that one of the advantages of AC circuits or AC power is that you can change the voltage from low to high or high to low by using something called transformers. And that made it possible for AC supply to be the dominant power supply, because you could transmit at high voltage and reduce the current loss and then step it down to the required value whenever you need it. So let's come and understand that particular device. So imagine that you have an iron core, okay, of this type. So it is connected, so it is a solid body, so there is a depth to this also, and it is fully connected to each other. Now you have a winding here like this and another winding here like this, okay. So we'll call this primary side and we'll call this as the secondary side, okay. So primary and secondary. Now if you supply a current here, okay, so if there is a current flowing here I, then what will happen is it will produce a magnetic flux. So there will be a flux produced here, and that flux, because it has an iron core, will be same everywhere, okay. So the flux linkage is 100%. So the flux in this coil and this coil that they are going to see is same. Now the number of windings or the number of turns here is NP and NS is the number of turns here. So this is the number of turns. So number of turns on the primary side of the device, and this is the number of turns on the secondary sides of the device. And let's call this current as IP, and you have a current here as IS, okay. Right now let's not worry about the direction of the current, okay, because that depends on the how the windings are placed. So you have IP and number of windings is NP, IS and number of windings is NS. Now you know that the flux linkage in any of these systems, okay, so the flux linkage is going to be equal to LI, NLI, okay. So, and that is also equal to, so NS into IS is equal to NP into IP here, okay. So we'll remove this, we'll write it proportional to, okay. So proportional to, and this is proportional to this. Based on this, we can say that NS-IS is equal to NP-IP because they are seeing the same flux. So secondary current divided by the primary current will be equal to number of windings on primary side divided by the number of windings on the secondary side. So that is one relationship we can get from here directly. The second relationship is that if there is no energy loss, then the power supplied here and the power being received here is going to be the same. Now let's say the voltage across this is Vp and voltage across this is Vs. So you can say Vp into Ip is equal to Vs into Is, and that's basically the power supply, okay, power. In other words, from here we can write Vs upon Vp, Vs upon Vp is equal to Ip upon Is, Ip upon Is. And we have already derived the equation here. So Ip upon Is will be Ns upon Np. So that is equal to Ns upon Np. So you could say that the voltage on the secondary side will be proportional to the number of windings on the voltage on the number of windings on the secondary side. So what we have got, the second equation we have got is Vs upon Vp is equal to Ns upon NP. So if you want to make a step up transformer, that means the voltage should be higher on the secondary side compared to the primary side, then you need to have more number of windings on the secondary side and less number on the primary side. And for step down, it should be the other way around. So this is basically the principle on which the transformer works. The assumption we made here was that the power is not lost, but in real transformers, power is lost. Okay, they are lost because of various reasons. First reason is that resistance of the windings. Resistance of the coils. Okay. So, because there is quite a lot of length of wire involved here, and these have resistance, and the current flows through that, and heat will be generated, and some amount of power will be lost. Okay, so that's number one. Number two is flux leakage. We assumed that the magnetic flux on one side is perfectly linked to the magnetic flux on the other side. However, that is not necessarily always true, because there could be air gaps inside the construction material, or there could be some openings where the magnetic flux, instead of being confined to the shell, the structure is such that some amount of magnetic field is also seen outside. So there will be some flux leakage. Number three is hysteresis effect. Now, during the magnetic property of materials chapter, we studied and saw that when this ferromagnet is magnetized and the magnetic field that is magnetizing is removed, there is some amount of residual magnetism that stays there. Okay, so which requires us. So when we try to reverse the direction, certain amount of coercivity is required. That means you have to give certain amount of magnetic field in the other direction to bring the magnetic field back to zero. And you may remember this curve of intensity of magnetization versus magnetic field intensity. And so when you started, it was like this, but after that, there is this curve, and this area under this curve, area inside this curve is the energy loss. Okay, and that energy loss can come out as something that will cause power. There will be power loss here, so efficiency will be reduced. The way you reduce that is by using very soft magnetic material. Okay, so soft iron. So for example, you can use soft iron. So that has lower coercivity and also lower amount of retentivity. Okay, but you want high relative permeability because you want to magnify the effect of the current. Okay, so high permeability, low retentivity, and low coercivity. Okay, so that is what will reduce this hysteresis effect. And the final reason for loss is eddy currents. So we again studied this when we were studying magnetic induction, that whenever you have a solid material and you change the current, not only do you have magnetic field, but you also develop current inside it, right? So those eddy current can also cause heat loss, and you can reduce that by lamination. So by using laminated, so layers of soft iron and laminated with some insulator in between, so that will make sure that the eddy current is reduced. So you can reduce all these effects, but you cannot eliminate it. So resistance of the coil, for example, you can eliminate by using thick wire. Now all this is going to, of course, increase the cost of the product, right? So your transformer cost is going to go up when you use thick wire, use soft iron of high quality, and you try to design it properly to prevent flux leakage, and you laminate. But so you have to make a call between whether it is better to lose some amount of power or to spend a lot of money in trying to build a very perfect kind of transformer. Okay. So, so that covers all the theory that we need for this chapter. In the next video, we will start with solving problems from CBSE board, JEE and NEET. And while watching those problems, if necessary, you can come back to these videos and watch them so that anything concept that you don't remember, you can use them. All right. So we'll stop here with the theory, and next video we'll start with our problems. Okay. All the best.